Okay, last problem. And for this one, we have a bullet fired into an at-rest pendulum bob, goes all the way through the bob and exits with a speed of v over 3. This variable 3 here, because I can't, I want to solve this in variable form, that number 3 is variable for all of you guys. So I'm going to call that, let's call it, y. Okay, so that 3 is going to be a y in this case. Um, so my pendulum bob is attached to a rigid pole of length L. The reason that rigid is significant there is that rigid implies that you can assume constant radius of the circle that it moves in. What is the minimum value of V such that the pendulum bob will barely swing through a complete vertical circle? We've done problems like this before. What this means is that we're going to assume that at the top of the circle that the velocity is effectively zero. Barely makes it over the circle would imply that the velocity is just infinitesimally greater than zero. So let's just set it at zero. We are allowed to use the mass of the bullet, the length of the bar, G, and the large mass in our answer as well. So, two things at play here, right? We have momentum during this collision, and then we have energy as well. So, we can set up two separate equations for these. Let's talk about momentum first. So we have momentum just before the collision is going to be equal to momentum immediately following the collision. Pre-collision, the only momentum comes from the bullet, so that would be m times v. After the collision, we have the bullet and the moving bob. So that, let's call it bullet, would be m times v over y. That's my new exit speed of the bullet, plus the mass of the bob times its final velocity. Let's call it v big M. So this is my conservation of momentum equation. And in this case, what I'm looking to solve for is this v, right? That's my velocity that I'm going to be looking for here. For energy, we're looking at the energy before the collision is going to be equal to the energy after the collision. So what that would look like is before the collision, you have kinetic energy of the bullet, little m. After the collision, you have the energy of the bob at the highest point, so UG of big M, and you have the final kinetic energy of the bullet, little m. So that would be 1/2 little m v squared equals big M times G times H plus 1/2 times little m times v over y squared. Now, that h, the height here, is also known. It's going to be double the length of the rod. So that's 1/2 little m v squared equals big M G times 2L plus 1/2 m times v over y squared. Okay, and so what I'm looking for here is to solve for my little v, and in order to do that, I'm going to need to look at the velocity of big M, right? I'm going to need to find an expression here to substitute in so that I can then solve for lowercase v. And so looking at my other equation over here, I don't have a velocity of big M over here. Instead, I know that that GPE here, the gravitational potential energy at the highest point, is going to be equal to the kinetic energy of the block right after the collision. So that's to say that the kinetic energy of block M at the lowest point is equal to the gravitational energy of the block at its highest point, which would be 1/2 big M times V of big M squared equals big M times G times the height, which is 2L. Solving for V of big M, I would get Vm equals 4GL and then the square root of that. So now that I have that value, I can take this and substitute it back up here. And I would get M times V equals M times V over Y plus big M times the square root of 4GL. And then I can solve this for the little v. So that would be mv minus mv over y equals big M square root of 4GL. Factor out that v, and I would get v times m minus m over y equals big M square root of 4GL. And then lastly, v equals big M square root of 4GL over m minus m over y. And that would be my final answer. So this is the first I've actually looked at this problem. And in looking at it, this whole section that I did right here is technically not necessary. I was just thinking of it like, okay, I'm going to have to set up some energy equation. This is where my brain went. It turns out that that's not actually required to finish the problem, and that instead, this is the work that I want to be working with. But sometimes that's how it goes with physics problems. Like your first thought's not necessarily the correct one, and then you just try to find another way to fix it. So I guess that's process in action for you guys. Anyways, have a wonderful rest of your day and enjoy this video key, and I'll talk to you guys soon. Bye!